to all the organizers for giving me this opportunity to present this work of mine. And special thanks to the main two ingredients of my talk, which will be, let me share my screen at the moment. So is my...
yes, your screen is visible.
Okay.
And your cursor is also visible.
Okay, so yeah, so since I'm sort of I'm actually the last speaker of this session, I would really not like to overburden you with a lot of mathematical details, etc., etc. But the paper which I am going to present, which already Chaudhury mentioned, that it's about entanglement dualities and supersymmetry. It has two main ingredients. One is entanglement, which is sort of aligning with the spirit of the present conference. And then there is supersymmetry. And then I realized that there was a talk from Aradha Shukla, who probably already introduced supersymmetry to some extent. And entanglement is something I suppose the audience is by now very well familiar with. So that sort of gives me some amount of relief of from introducing these two concepts in very great details. But still, I would for the sake of the present talk, I would give you some brief introduction on these two elements. But before that, before going to the main talk, let me introduce my collaborators. I mean, So this work is done in collaboration with these two gentlemen. One is Robert, who sort of, I had a discussion with Robert from which basically the entire activity got nucleated. And the other person is Lucas, who is currently in Melbourne. And I think they sort of took a very driving role in this entire project. Let me give the outline of the present talk. So I will still start with a very brief introduction to supersymmetry, which is relevant for the present talk. I will, of course, I cannot give you an introduction to supersymmetry. That will probably take a whole long conference. But I will only explain I will explain certain aspects of supersymmetry which are relevant to me to explain the physics of this work. Then I will give you the example of the supersymmetric quantum harmonic oscillator, which is I think to some extent already introduced in the talk by Aradhya. Then I will come to Gaussian states, which I'm not sure if the audience is already familiar with the Gaussian states, but probably the audience is familiar with the definition of Gaussian states, where we find them. And I will describe how supersymmetry connects between different Gaussian states from different systems, from different fermionic and bosonic systems. And there also I will give you an example of these. I will bring the example of harmonic oscillator again in that context. Then I will move to the entanglement description. Entanglement, I will try to give an elaborate account of entanglement in Gaussian states. I will describe how these entanglement identities, how there are new entanglement identities induced by supersymmetric maps between different fermionic and bosonic systems. And to the very end, towards the very end of my talk, I will give an example. I will illustrate this this finding with an example of GITA honeycomb model, which again I think is introduced by Bhaskaran in the conference. So probably the audience is again familiar with the GITA honeycomb model to some extent. And finally, I will point to a very peculiar finding of entanglement in the bosonic version of these GITA honeycomb model, which is basically a model of Majorana fermions. So if you look at the supersymmetry related bosonic counterpart of that model, you will see that there is a peculiar feature in the entanglement, which I call a super area law. I will explain all those things towards the very end of this talk. Okay, so with that, let me start with a very brief introduction to supersymmetry, as I promised, and also what is relevant for us. I found there are lecture notes by Adlal Bilal, and these are available on archive, where he has sort of given a very nice introduction why we should read supersymmetry, etc. I'm not going into all those details, but I have sort of picked up two important sentences from that lecture notes in such a hurriedly made slides. So the first thing is that supersymmetry has not only played a most important role in the development of theoretical physics, in several branches of theoretical physics over the last 3 decades, but that has also strongly influenced experimental particle physics. Even though we do not, we believe, we still see that supersymmetry is unbroken in the present universe. There are a lot of experimental activities nucleated from theoretical findings of supersymmetry. And secondly, it's not only restricted to particle physics, but it has appeared outside the realm of elementary particle physics and has found wide applications in several condensed matter systems, including disordered systems in which there is a very strong influence of supersymmetry, and also other systems, and also other condensed matter models, including spin systems, and the recently discovered topological mechanical systems. So yeah, the upshot is that supersymmetry has been exploited as a very useful tool to analyze physical properties of systems which are related to their single particle eigenstates. Before going into that details, let me briefly explain the supersymmetric quantum mechanics, even though when we talk about supersymmetry, we immediately jump into the field theory, where we realize supersymmetry as an extension of the Poincare algebra. But still, we can realize supersymmetry in a much simpler model, which is more close to our heart from our high school days. That's quantum harmonic oscillator. I think we understand quantum harmonic oscillator to a very great extent. And the Hamiltonian, which describes this quantum harmonic oscillator, is given by this form that you have an anti-commutations of this B dagger and B, where B describe the annihilation operator. Basically, B and B dagger together describes the ladder operators of the in this context. They have a commutation relation, which is given here. And that's basically the bosonic quantum harmonic oscillator. We know the spectrum. We know there is an offset, which is given by half of omega, the 0-point energy. We can similarly realize a fermionic version of the quantum harmonic oscillator. And there is, and it's quite similar. It's just that the Hamiltonian of the quantum harmonic oscillator is now expressed in terms of fermionic ladder operators, which have anti-commutation relations instead of the bosonic commutation relations. And then they have you can see that in the Hamiltonian that the role of this commutation is sort of reversed. So now the Hamiltonian for the fermionic oscillator is expressed as a commutation of this fermionic degrees of freedom. And you find that there is in this system also there is an offset in the energy, but which is exactly opposite to the bosonic offset. Basically, if I add these two systems, I get a supersymmetric, I can write down a supersymmetric Hamiltonian, which has the bosonic part and the fermionic part, but now there is no offset. That implies the ground state energy of a supersymmetric Hamiltonian, of this supersymmetric Hamiltonian, is 0. In fact, the ground state energy for all supersymmetric Hamiltonians are 0. Otherwise, we call the supersymmetry is broken. Interestingly, this Hamiltonian, when I add them together, like when we have both the elements present in the Hamiltonian, we can write down this Hamiltonian as a commutation of a supersymmetric charge, which I call Q here. This generates the supersymmetry transformation. This is called a supersymmetry charge. And you can actually get a very compact expression for the supersymmetric charge, which is B dagger C. What this means is that in terms of the single particle states, it sort of maps Fermi onto bosons and vice versa. And as I said, the ground state energy of a supersymmetric theory is 0. Having said that, let me now move to the Gaussian, the description of Gaussian states, and there I will also explain how supersymmetry identification maps are useful to map from one Gaussian states from a fermionic system to the Gaussian states of bosonic systems and vice versa. I'm not following the questions raised from the audience. So if you have any questions, please stop me at any point of time. And if you have questions, then I will be happy to answer them. Otherwise, I'm sort of continuing. The Gaussian states are interesting in the sense that many analytical and they can be solved analytically, and many analytical expressions can be obtained which characterize the physical properties related to these Gaussian states. The name Gaussian states are, the name Gaussian is related to the fact that for bosonic systems, these Gaussian states are actually characterized by a Gaussian Wigner distribution. While for fermions, it's a bit indirect. It says that when we compute higher order correlators, you can always Wig decouple, or you can use Wig theorem to decouple them in terms of simple 2-point correlators. So example of Gaussian states in bosonic system is ground state of quadratic bosonic Hamiltonians, while for the fermions, all eigenstates of quadratic fermionic Hamiltonians are Gaussian. Examples could be integrable models, Ising spin chains, etc. But before now, so far in the previous introduction of when I gave the introduction to supersymmetry by using the model of quantum harmonic oscillator, it was a single mode description basically. Now, when I want to move to multi-mode description from the single mode description, and that's quite straightforward. But before doing that, I need to define a basis of operators which are relevant to describe the theory of bosons and fermions for me. So I can either work with a Nambu-like basis, which include both creation and annihilation operators for bosons and fermions, or I can actually define a new basis in terms of the real operators, and this is more useful for the rest of the talk. So that's why it's important to introduce these operators at the very beginning. So these operators for the bosons are called quadrature operators, which are basically P operator or Q operator that can be explained as momentum, canonically conjugate positions and generalized positions and generalized momenta. Or for the fermions, we can introduce Majorana operators, which are again combinations of the complex fermions operators. So for a particular flavor of fermions, we can have two different flavors of Majorana operators defined that way. And we can now redefine the basis in terms of these real operators, which I call a quadrature basis here. For bosons, it will include Qs and Ps. For fermions, it will include these Majorana fermions. And the canonical commutations and anti-commutation relations in the new basis take this form, which is quite simple if you think of these quadrature operators. And because of this simple structure of the canonical commutation relations or the anti-commutation relations, which are encoded in these two matrices, which is omega matrix and the G matrix, I will later come to these matrices repeatedly in the rest of my talk. But these matrices take very simple form in this real basis. And with that definitions, I can now formally introduce a Gaussian state, which is defined as the solution of this equation, which I have written here. And a solution of this equation exists when the J square is -1. And there are further two more conditions required, that for bosons, the capital G matrix represent a metric. That means it has positivity. And for fermions, the omega is a symplectic form. That means in the language of mathematics, that means a skew symmetric matrix which is non-degenerate. So then I can, that sort of, is the screen still visible?
Yeah, we can see your screen.
Okay. Okay. So, with that definitions, we can now see that each Gaussian state has a Kähler structure, which is given by this triplet, capital G, capital omega, and capital J, and they have these relations, which are very well known. And the entanglement of it, and the matrix J plays a very crucial role, because the entanglement of a Gaussian state is entirely encoded in this linear complex structure called J. So that's part of the Kähler manifold, which describes a Gaussian state. So whenever we will talk about a Gaussian state, we will refer to this triplet, and particularly when we will talk about the entanglement encoded in a Gaussian state, we will show how this matrix J encodes the entanglement spectrum, encodes the details of the entanglement spectrum. Okay, so with that, let me now continue with the description of a multimode supersymmetric quantum system. Previously, when I introduced the quantum harmonic oscillators, we had one mode, and now we have a basis structure which includes the different modes in the problem. And we can now define a supersymmetric operator, which earlier was much simpler. I will again come to that example of quantum harmonic oscillator later in the talk. But let me formally introduce the supersymmetry, which is relevant for me to describe an n-mode quantum system, which includes both bosonic and fermionic degrees of freedom. The supersymmetric charge operator can be written in the following form. You see that it involves both the bosonic basis given by xi hat A with the subscript B, and also the fermionic basis, which is given by the subscript F, and and then there is a matrix R, which we take to be real because we are actually dealing with real operators, sandwiched between these two bases. With this charge operator, we can now generate a full supersymmetric Hamiltonian, which will be, because Q is now Hermitian, it is basically Q squared. The supersymmetry operator is just Q squared. And if we complete the algebra, we find that there are two pieces. This full supersymmetric Hamiltonian decouples into two pieces. One is entirely in terms of the bosonic, one entirely describes a bosonic system, and the other a fermionic system. These two Hamiltonians are quadratic and decoupled with the simple form of the charge operator, which I'm showing here. Of course, if you have more complicated form of the charge operators, you will have more complicated form, but our entire analysis will be restricted to this type of simple form of the charge operator. Of course, R can be more complicated than just for the n-mode system. And we will actually later, towards the end of our talk, we will actually give you a physical meaning of this R operator when I will flash some examples of real physical systems. With that setting, if we now, we can see that the full supersymmetric Hamiltonian has two pieces. One is the bosonic Hamiltonian, which is given in terms of the R and the G matrix, while for the fermionic Hamiltonian is given in terms of the R and the omega matrix. What are the excitation spectra in these two systems? It turns out that the excitation spectra can be simply solved by computing the Heisenberg equation of motion. And if we do that, we find that the relevant matrices whose diagonalizations lead to this excitation spectrum in these two systems are given by this KB and KF. where KV now includes both the omega and the G matrices, and particularly this combination of R, and KF is given by this combination of R. Even though the combinations look different, we can easily show that the spectrum of KB and KF, the spectra of KB and KF are similar, except the zero energy modes present in the system, if any. That's because the nullity, that's because the kernel of R and R transpose can in principle be different. So that's why they can have different number of zero modes present in the systems, which are actually given from the nullity of R versus R transpose. But the finite energy spectrums the finite energy spectra are exactly equivalent between KB and KF. So we call that KB is isospectral with KF, except for zero modes, as I said. The full supersymmetric Hamiltonian can now be expressed in terms of the eigenenergies and the normal modes, which I have written here. I have tried to minimize showing a lot of mathematical details, but I think these are like some of the simple equations which are helpful to understand the problem for this n-mode system. The earlier
Krishanu, a question here.
Yeah, sure.
So it's probably because you started with a quadratic Hamiltonian, it's probably not surprising that it is solvable. But there is something more to it. What is that more? I mean, that's what I'm missing.
So I'm not starting with the quadratic Hamiltonian. I'm starting with this charge operator.
Right, but you have only quadratic terms, right? A daggers and A. You have nothing else. So
no,
finally,
exactly.
So it should be diagonalizable in principle. Nothing's to maybe there will be complicated terms, but after all, this is bilinear of operators.
Yes,
I can always,
the Q charge operator.
Right.
Yes,
so
yes.
I think the symmetry is probably, maybe the solvability is not interesting, but the symmetry is interesting. I'm just trying to distinguish two things.
So yes, the charge operator itself is diagonalizable, but what I am interested at is the Lie generators that basically generating these transformations, because those eigenvalues give the eigenspectrum. So of course, if you want to see the supersymmetric correspondence between the spectrum, you will see there the spectrum is actually between KB and KF and not between HB and HF. And actually, there are when I'm not sure I will be able to show this in this talk, probably not. But actually, you can realize this entire prescription on a lattice, and then you will see that there are physical meanings associated with the charge operator, the HB, and the HF. So all of them actually represent Hamiltonians, but on different lattices.
But the whole formulation Hamiltonian is a Gaussian theory. It's a solvable theory.
Yes, of course. Yeah.
Okay, so there are no interactions, and I mean.
No. Of course, yeah.
I'm just trying to understand the power of this method.
Absolutely. So I am still avoiding any interacting problems in this picture. Of course, if you
so there is supersymmetry, but it's at the level of quadratic Hamilton, single part.
Exactly. Yeah, that's true. And of course, if you take a more complicated charge operator, you will be realizing models which are non-interacting models. But I'm not sure to what extent you can sort of analytically solve them. Of course, there are supersymmetric maps that connect between two mean field Hamiltonians. That's one possibility.
Yeah.
But again, that has been already mean field decoupled. So brought down to quadratic level.
So here the entanglement. So I mean, just one more remark I'll make just to understand things. So I think we know that fermions are Slater determinants when it is a multi-particle fermions, and bosons has to be fully symmetric. So given this information, which I already know, Are you saying that there's a supersymmetric connection between the wave function, which is a filter determinant, and a wave? I think you have more than that. I think what I'm trying to say is that if I look at an n particle, fermionic Hamiltonian, if it is free, it will land upon on a Slater determinant, no matter what other details are there. And a boson is fully symmetrized wave function. And on top of it, you are putting additional structures. Is that correct?
Yeah.
Because I kind of know for free fermions and free bosons, they are extremely entangled because they are fully symmetrized or anti-symmetrized.
Yeah. For Majorana fermions, the story is a bit different.
Sure. Okay.
Yeah. So I will come to the.
Okay, fine. Thank you. Just a clarification, so that because it's a very different subject, and okay. Please go ahead.
So I will. So that's why I'm from the very beginning. I'm sort of resorting to this basis in which the fermions are given by Majorana fermions, and the bosons are given by these quadrature operators, the real bosonic operators.
Right,
so later, when I will actually talk about fermionic systems, you will see that I'm actually talking about Majorana fermionic systems, and whose bosonic counterparts can be given in terms of these Q's and P, so that.
Oh, that's very interesting, because this is like a fractionalization of a fermion into this two in the pair of Majorana fermion, which is non-trivial topologically.
Yeah.
And then you are finding counterparts of the Majorana fermion in the bosonic language. Okay, exactly. That's a very non-trivial. Okay, fine. Exactly. So that makes it very non-trivial. Okay, fine. Please go ahead. Okay.
Oh, thank you. So I think with that, so now that we know that what is the full supersymmetric Hamiltonian, we know we can express the full supersymmetric Hamiltonian in terms of the eigenenergy and the normal modes both in the bosonic and the fermionic system. We know that the ground state is of the full supersymmetric theory is a tensor product, simple tensor product between the bosonic tensor product of the bosonic Gaussian state and the fermionic Gaussian state. And as I said, for each Gaussian states, I can give you a linear complex structures J, which I flashed somewhere here. If you compute the J here, you will find that these J's are related to the J's are related to the Lie generators, which are given by this KF and KB. And so the picture is the following now. Given that supersymmetric chart, which I'm showing here, it induces a supersymmetric identification maps between the bosonic and the fermionic phase space. So let me call the bosonic phase space to be VB, which is R2N for me, because we are dealing with real operators. The fermionic operators, the fermionic phase space is also R2N. And then the maps are the following, that so the supersymmetric identification maps is T1, which acts on VB, give me VF. And there is another reverse map, which is T2, that acts on VF, give me VB, like a state in VB. If I now want to preserve the...
Just a clarification question.
Yeah, sure.
So your bosons are hardcore bosons, are they?
So I'm not restricting them to any hardcore. So my bosons are real operators, which are P's and Q's.
No, because, okay, thanks.
So I will explain that to you in one of the next slides. You might be able to get it much better.
But I think, Krishanu, maybe it's an interesting point, because if the bosons are hardcore bosons, at least in one dimension, they will practically become like fermion in some sense. And then what redundancy that brings in is an interesting question, probably.
So I would still say that it's so when you say that the bosons are sort of mapped to hardcore fermions, you think of in back of your mind, you think of this kind of Jordan-Wigner transformation between these hardcore bosons and fermions. But I think this is more than that. So that's a very specific thing.
Sure.
1D. And of course there are generalization in 2D, etc. But this is still not assuming any hardcore boson, any hardcore constraint on the bosonic field.
Yes. Yeah.
So when I described the fermions and bosonic spectrum in the very beginning, and let me go back to the previous talks. For example, for the supersymmetric harmonic oscillator, my NB still can take any values between 0 and infinity, while NF will still take values between 0 and 1. So from there, so basically what the supersymmetric maps are saying is the following, that if you have an eigenstate given by VB of the matrix KB, which satisfies this equation, these equations, then the identification map T1, which acts on the bosonic space. Here you can see it's acting on the bosonic space. And that gives another state which is in the fermionic space, but corresponds to the same eigenvalue. And that also holds for the other map, which is given by T2, but that now acts on the fermionic space. Now,
Krishanu, if this mapping is one-to-one, should we have particle number conservation, or that's not necessary? You can violate that. I mean, that probably that's though you said that fermions, of course, one level, one fermion. That's completely correct. Yeah. Bosons can be many, but now if you want to really have a one-to-one mapping at the level of Hilbert space, do you need same numbers, or that's not necessary?
I think the occupation at each state is still 0 or 1 for fermions, and it can be anything for the bosons, but it's still the map. Yeah, and one more very important point is that it's a map between finite energy states. I cannot define such map for zero energy state, and you will see why it cannot be at the very next slide. You will see that now, if I want to preserve the commutation or anti-commutations of the maps states, we'll see that the T1 should be normalized appropriately, where this kf inverse to the power half it's a matrix notation, but basically, if we can diagonalize, you will see it. So basically, this notation says that, perhaps I can annotate. So basically, the notation says that for any matrix, do you see my annotation?
Yes.
Okay. So basically, that says that if you have diagonalizations, the mapping holds at the level of the eigenvalues. So that's the definitions. That sort of describes what this thing is. So this kf inverse to the power half is basically at the level of eigenvalues, implies that the eigenvalues are used in the normalizations here. 1 over that eigenvalues. So this normalization is merely done to preserve the commutation or anti-commutation across these supersymmetric identification maps. And then a further identification appears is that if you apply L1 and L2 together, you see that you get back the linear complex structures in each of the vector space individually. So basically, if I apply L2 on the fermionic space, it takes me to the VB, and then I apply L1, it brings me back to VA, and that essentially gives me the complex linear structure in VA, and the same holds for the VB as well. So once we now identify these supersymmetric maps, let me give you let me erase this. Let me now give you the example of what's happening at the level of simple supersymmetric quantum harmonic oscillator. The charge takes extremely simple form, which is there. And if you compute the supersymmetric Hamiltonian, you will get that it has 2 different pieces. Both the pieces are very familiar to us. The first one is basically the bosonic piece. And the second one is the fermionic piece. Previously, I shown you the same form in terms of B dagger, and CNC dagger. If you compute the Lie generators for them, sorry, there is a typo here. Both the KB and KF turn out to be the same, and they have this simple form in terms of the matrix form is this. From the same prescription as I gave you, if you compute the maps, the normalized maps, you will see that they also have very simple form. And what they do essentially is that if the map acts on the gamma Majorana operator, gamma type Majorana operator, they give me Q type bosonic variable. If L1 acts on the eta type Majorana operator, they gives me P type bosonic variable. And the same thing applies for the other map given by L2. And you can verify that the commutation relations and the anti-commutation relations are preserved across these maps. With this, let me now come to the entanglement description in Gaussian states. So, and that I said in the very beginning that this entanglement in Gaussian states described by these matrix J can be entirely explained in terms of the, can be entirely written in terms of the matrix, in terms of this complex linear structure. I think this is, since this is the last talk of a conference, which is of a conference and school which is dedicated to quantum information and quantum technology, I think everyone is super familiar with the bipartite entanglement so far. Let me still flash the definition once that for a pure state psi, the bipartite entanglement is characterized by the spectrum of a reduced state, or what is sometimes called a reduced density matrix, is given by this rho A, where I have traced over the environment, which is denoted B. And then if it is a Gaussian state, then I can get analytical expressions for this bipartite entanglement that and we find that this rho A can be written as an exponential of a Hamiltonian operator. And this Hamiltonian operator takes these forms for a bosonic system and the fermionic systems, and you can entirely calculate the matrix Q, the Hamiltonian matrix, in terms of the capital J. Of course, you already know the capital G and capital omega for these systems. There is one more thing I want to say, that we know that when we quantify this kind of bipartite entanglement, one measure is given by von Neumann entropy. Of course, there are other generalizations of this von Neumann entropy, including other forms of Renyi entropy, for example, but all of those forms can also be written in terms of capital J. The von Neumann entropy can be written in a very simple and compact and unified form, which applies for both the bosonic and the fermionic systems, that it involves this J matrix in the following way. And it turns out that the eigenvalues for the capital J matrix, they are restricted between 0 and 1 for fermionic systems, while they are between 1 and infinity for the bosonic systems. And we will see a very interesting form, a very simple relations between these two entanglement entropy when we invoke supersymmetry between fermions and fermionic and bosonic Gaussian states. But before that, before going into showing you the entanglement duality, which is the main thing of this, the main element of this talk, let me formally define the subspace here. You can see that if I for a vector in the subspace in the space V, the subspace is spanned by all these vectors which satisfy the conditions for the bosons, and that's also important. That also says that the subspace. It's also important that the subspace is spanned by even dimensional vectors, because for the fermions, otherwise, for the bosons, the determinant of this Q symmetric form will be 0 if it is odd dimensional. And once we define the subspace with this way, so it's kind of projection onto a particular subspace I'm interested at. Once I define that subspace using these relations, I can see that the matrices which are relevant for me, these omega matrices and the G matrices, they can also be written in a block diagonal form, which is given by these capital omega A and capital omega B. So I can restrict the structures entirely in terms of subspace and the environment, while there is no mixing between them. Once that is done, I can now formally present the main propositions of the duality, which which we have explained in the paper, which in our paper. I think the link is. I have given it in the very first slide, but it's not here anymore. But still, let me state the propositions which I want to mention here is that for a supersymmetric system which has a phase space given by VB and VF, both equipped with scalar structures, that means the scalar triplet capital G, omega, and J, both of them. And for two inequivalent decompositions of the full phase space, namely this A with capital B and A with capital BF for the bosonic and the fermionic subsystem, there are reduced states associated with them, which are given by the density matrices rho boson on the subsystem A and rho fermion on subsystem A. And these two reduced states are Gaussian, and they are fully described by the restricted complex structures, which is given by this capital J A for the bosonic system and the fermionic system. And they satisfy this relation that one is the negative inverse of the other. So I can similarly write down the other formula in terms of B and F. So basically, that at the level of eigenvalues that say that the eigenvalues which are restricted between 0 and 1 in the fermionic subsystems, they are one-to-one mapped between the eigenvalues and the bosonic counterpart, which are now which can now vary between 1 and infinity. So there is a one-on-one correspondence which is given by this entanglement duality induced by the supersymmetry. This is strictly a correspondence between two systems which are supersymmetry identified. This implies a corollary. My screen is frozen. Hello?
Yes, Krishanu, we can hear you. I don't think it's a communication problem.
My screen is.
Maybe you close it and reopen.
Yeah, let me do that.
Just to give you an idea of how we are doing in time, we have 15 more minutes.
Okay, yeah.
And maybe if you finish in like 7-8 minutes, then we'll have some time for questions.
Yeah, sure. So is my screen visible again?
Absolutely, it is.
Okay, so that's the main proposition which I wanted to mention here is that if you have so the restricted complex structures satisfy this relation, and that implies a corollary for me, which is the following: is that you recall the phase space structures and the identification maps which I showed to you before. That I have a bosonic phase space VB, I have a fermionic phase space VF. The normalized identification map induced by supersymmetric charge operator is given by L1, which takes me from the bosonic sector to the fermionic sector. There is a reverse map, which is L2, which takes me from the fermionic sector to the bosonic sector. And then if I have a bosonic subsystem within VB, then the L1 acting on that subsystems will take me to VF, and it constructs a subspace within the VF, which we call a dual fermionic subsystem. The restricted linear structure, which is for the VB, which is exclusive for VB, that is also mapped to our restricted linear structures via this L1 mapping. And these two restricted linear structures are related by this formula. There is another formula which I'm not showing here. You can similarly prove that there is another formula in terms of the L2, which relates the other way. But this formula immediately says that the spectrum of the two restricted linear structures satisfy this condition because their trace and determinants are the same. And so let me show you the plots of these two entanglement entropies as a function of lambda, which will be the eigenvalue. You can see that if I now plot the eigenvalue, if I now plot the entanglement entropy in terms of the eigenvalues of the J from this formula, and I can see that that the fermionic systems is restricted between 1 and 0, with 1 being the maximally entangled case. And you can see that when the fermionic system attains maximal entanglement, the entanglement for the bosonic system diverges. And that's because of the identity which I'm showing here. So far, this is still a little mathematical, but I would like to illustrate this by an example, a system in which people often look for entanglement. They theoretically measure different quantities related to entanglement to characterize the topological order in that system, and the system is known as GITA honeycomb model. It is basically a. I know that there was a talk by Ganpati Bhaskaran in the conference where he very nicely explained almost all details about GITA honeycomb model, including the correlations features in those models, etc. So I'm skipping that details, but let me still briefly describe what the model is. This is a model of a frustrated spin system which has bond directed spin interactions given by X, Y, and Z. So in principle, there can be 3 different. So it's a model. The spins are on this honeycomb lattice, and they have bond directed interactions given by JX, JY, and JZ along these 3 different bonds. These are called these GITA couplings. And this model, as GITA realized that these models can be solved by casting the spins in terms of Majorana fermions. And when you write down the model in terms of the Majorana fermions, you realize that it's a model of Majorana fermions hopping on the honeycomb lattice against a static Z2 valued gauge field. So the gauge field is frozen and the Majoranas are hopping against a frozen value of that Z2 valued gauge field. So the gauge field can only take value between 1 and 0. That's why it's Z2 value. In this model, this Majorana model can be generated from a supersymmetric charge operator, which I have written here. Here you can see that the R matrix, which I showed in the very beginning, which appeared to be an abstract matrix when I started this description, but this R matrix has a particular meaning here. It is basically given by the connectivity matrix of the honeycomb model. So R matrix essentially encodes all the connections between the honeycomb, all the connections on the honeycomb lattice. And you can see here, the way I have written it here, you can see that for the GITA model, the Hamiltonian was between 2 different. The Hamiltonian was about a Majorana hopping between 2 different sublattices of a honeycomb. So, for example, let me try to illustrate it a bit more. This is the honeycomb, basic honeycomb structure. There are eta fermions. There are gamma fermions. These are explicitly on the 2 different sublattices, and there is hopping between these 2 fermions given by the GITA Hamiltonian. Here you can see that now that this capital A describes a connectivity matrix, you can see here that since gamma and eta are sitting on different sublattices, Q and P are actually sitting on the same sublattices, which are same as the eta sublattices here. So basically, in this description of Q, both P and Q are sitting with the eta fermions, while the gamma fermions are connected by one of these quadrature operators via the connectivity matrix. This is the connectivity matrix, which is taking the gamma fermions from one side to the other. Let me erase that. Again, if you compute the full supersymmetric Hamiltonian, it will be decoupled into 2 pieces. The fermionic pieces will be the GITA Hamiltonian, and the bosonic pieces will be on either of the triangular sublattices of the honeycomb lattice. Here, if you now calculate the entanglement between 2 subsystems, you will see that. So for example, if I take a subsystem from on the honeycomb lattice, I map it via the L1 inverse on the bosonic systems, and we find that there are very interesting properties revealed by this mapping, particularly the entanglement. First of all, we know that on the fermionic systems, the entanglement has show an area law behavior. That means it grows with square root of the number of sites within the subsystem or the area of the subsystem. And that's evident from the next plot. The left-hand side is for the fermionic systems. I will come to the right-hand side later. For the fermionic systems, we see that if I now take a parallelogram-like cutoff to define a subsystem, which for example cut through these three types of bonds. There are three bonds, as I said, Jx, Jy, Jz, and these are the values of the coupling along those bonds. So if my parallelogram cuts no strong bonds in the fermionic systems, the parallelogram cuts no strong bonds in the fermionic systems, I see that I certainly expect an area law in the fermionic problem. In the supersymmetric identification maps also show an area law in the corresponding bosonic system. So both of them are showing area law scaling when the parallelogram is cutting no strong bonds. However, if the parallelogram is oriented in a different way, we still see that from the fermionic system we expect simple area law. That's independent of the cut of the orientation of the parallelogram and also the shape of the parallelogram. But that area law translates to a super area law behavior in the bosonic system, particularly when the parallelogram is cutting strong bonds in the model. And the reason is that in that case, we expect in the fermionic systems, there are maximally entangled modes, which are highly localized along the boundaries. But even though that implies localized modes on the supersymmetric bosonic system, the entanglement diverges because of the maximal entanglement in the fermionic sector. In the bosonic sector, the entanglement diverges. There are many modes that corresponds to, there is a finite fraction of modes that corresponds to this diverging entanglement, and that results in the behavior which we call a super area law, which is bounded between the area law and the volume law. And that's something which is a specific feature of the bosonic system, which is supersymmetry related to such fermionic systems. Of course, in normal bosonic systems, we do not expect this behavior, but because of this particular supersymmetry relations between the bosonic and the fermionic systems, we see this peculiar feature in the bosonic subsystem coming up. I think here I would like to stop and would like to take questions from the audience. And thanks to everyone for your attention.
Okay, Krishanu, thanks a lot for this very, very intriguing talk. I have just too many questions in my mind, which I will not ask. Okay, so the floor is open for questions. Please unmute yourself and ask.
What is the physical meaning of the super area law?
So I think it's a little difficult to attach a physical meaning to the super area law behavior. It's appearing because of a particular orientation of the subsystem. So all I can say is that if you change the orientation of a subsystem on the fermionic sector, then the supersymmetry map can give rise to certain bosonic modes which have diverging entanglement, and as a result, we get the super area law. So it's an orientation-dependent phenomena on the bosonic side.
Okay. Fascinating talk, truly fascinating talk. I mean,
coming from particle physics and field theory background, right, Prashant, you must be amazed that people now bring these concepts to such, right? I mean, it's like so incredible.
And so clean also, you know, so beautiful.
Yes, that is true. Yeah, extremely clean. Yeah.
I sort of wanted to explain a bit more about the details of how you understand the maps, but I thought that being the very last speaker of the conference, I shouldn't really.
No, actually, it's not that. It is just that we are also like, most of the audience probably is Indian participant. And it's 9:30. I'm amazed that there is still 109 participants.
Yeah,
It's
really.
absolutely unbelievable.
Oh, I
Really hats off
didn't
to
know
them.
that.
I mean, really,
Yeah.
it's unbelievable. So maybe I ask just one quick question and then
Yeah, sure.
So you see, I think you said something very interesting. That maybe the super area law, I think probably is related to the fact that the entanglement is really long ranged. So more sites are getting connected, so that it's not just lying on the neighborhood of the boundary. If you cut something, you expect the area law because it's on the boundary, right? It's not that long range.
Yeah.
And now if it starts percolating into the bulk, then it exceeds the area.
Yeah, exactly. So
It's
the localization changes actually.
Yes, so the entanglement is not localized; it's more delocalized in a sense.
Yeah.
Probably that's the. But my question is a little different. I think it's very intriguing what you said. I mean, you converted the fermions into these fractional objects, which are Majorana fermions.
Yeah.
And then you are integrating out things, which basically means if I have some original physical fermions in mind, you have broken them into two pieces each.
Yeah.
And then you are choosing some even number of them for sure. Probably you should not choose odd, and integrating it out. Which is like saying that from the original realization, I am randomly fractionalizing certain electrons, and from them I am taking these Majoranas and integrating it out.
Yeah.
So of course, in a physical system which is only comprising of fermions, I cannot even imagine how I integrate out in it. Of course, mathematically you can do it. The physical meaning is very hard to. So I mean, I'll put it this way: that when in fractional quantum Hall, an electron fractionalizes into it's like saying quarks. To think of quarks, and like quarks each come with 1/3 and 2/3 charges, and you are saying that the composite proton is comprising of quarks. But what I'm going to integrate, I have a soup of these protons, and I'm going to integrate out certain number of quarks from it, and look at the rest of the system, and then look at its supersymmetry. That's very non-trivial from the point of view of what you're doing with the Hilbert space of the problem.
I agree with you. That's particularly peculiar because my complex fermion is already fractionalized, and when I'm doing the cut, I'm sort of taking half of them inside the.
I think the rest is a mathematical change of basis.
True.
Right? I can always write fermions as Majorana fermions. Nothing stops me from. I think when you're integrating out, you're doing something really horrible to the problem, and that's what gives the new information.
So the thing is that even if you do it to the fermionic sector, you do not see any changes to the area law scaling.
Yes.
But now, if there is a system which can be supersymmetry mapped from that system, you see that there are this kind of cutting has non-trivial.
Which basically means that your fractionalized fermions are very much there. They are the right quasi particles, not the original fermions, but the fractions of them. And they are delocalized. So that's the non-trivial thing. So then there's meaning to this whole physical process. Thanks a lot, Krishanu, for this wonderful talk. And I think
one small question.
Yeah, please.
Is there any random matrix kind of a view of this, which may throw some light, because this power law type of behavior?
Yeah.
Typically I have seen some random matrix.
No, please go on. Prashant,
essentially I'm trying to see Arul. I remember Arul Lakshminaran had one PR paper some time back, and in this conference also, people talked about throwing some light on entanglement entropy from random matrix perspective, particularly. So maybe there may be something. I'm just curious. Nothing.
No, you are absolutely right, and it's a very good point. It's kind of the outlook of the problem. So you have sort of preempted the outlook in the thing is that what we are looking at whether we can explain this behavior from the eigenvalue distribution of the matrix J, which I said. So that eigenvalue distributions will be, if you want to analyze that eigenvalue distributions of the matrix J, the complex linear structure, there you will have to use the random matrix theory. And from there, you can show that in what situations you expect a super area versus an area scaling.
Fascinating, really beautiful. Yeah.
Yeah, that's something which I cannot show you right now. It's something which is under progress.
Great.
Okay, so with that, are there any other questions? Please.
There is a question in chat box. I hope.
Okay.
Oh yeah, I can.
Krishanu, can you please?
So I can look at the text box. It says that does the supersymmetric chart have any 0-point non-zero functions like the ladder operator gives non-zero 0-point fluctuations? No, for a supersymmetric theory there is no 0-point fluctuations. If I understood the questions correctly, it's raised by Deepon, and if I understood the question correctly, the answer is that the 0-point fluctuations cancel between the fermionic and the bosonic part. So there is no 0-point fluctuations in the supersymmetric theory. Should I move to the next question?
Are there any more questions, Krishanu?
Yeah, there are a few. Thank you for the lecture. Can you please suggest a few reference papers related to similar use of quantum information in particle physics? That's something which I cannot immediately tell you. I have to look at the reference list in our paper, but you will certainly find some references in our paper, which I have sort of, I can just, so it's a paper, let me just quickly give you the reference to our paper, and there, oh, I see here, the paper is published in PRR, so you can, if you look at that, you will find some useful references in that thing. But I think from the quantum information perspective, I think this is kind of the first work that relates the idea of supersymmetry to this kind of Gaussian states, which are very often used in quantum information.
Okay, so are there any other questions there?
I do not see any other question.
Okay.
So yeah.
Okay, Krishanu. So thanks a lot again.
Yeah.
And yeah, we hope to host you sometime physically in India after the Corona time is over.
Sure.
Thanks
I'm
a lot.
also very much looking forward to visit the institute again. I did it last time in 2019. I think I spent
you were there.
Almost like 2 to 3 weeks.
Yes.
But yeah, I would love to talk more about the work, and then if any of you find this interesting and want to know more about the work, I will be glad to share my experience and thoughts.
Sure.
And this kind of stuff, you can do a lot of Blackboard work also,
Yes.
Yeah, I actually, the thing is that I wanted to give a Blackboard talk because then I could probably explain more things in a much better way. But I wish I could be part of this conference from the very beginning.
Yeah.
But one good thing is that at least some of the speakers already introduced the main 2 ingredients of my talk, so that really helped me a lot.
Yes.
And particularly I saw Aradhya's talk, and then I saw Bhaskaran's talk.
Even Professor Khare, I think, talked about supersymmetry.
Oh yeah, I see. Yeah. I think he's an expert in supersymmetry. Yeah.
Yes.
Yes. So that really helped.
Yeah.
Okay, somebody thanking me.
I would like to thank you first of all. Okay, Krishanu, again, thanks a lot for the wonderful talk. And I think being the last session, I would really like to thank Professor Panigrahi for this wonderful school. I learned so much from it. I am a part of the organizing team, but my, I think, only contribution is to sit in the talk. I've done nothing practically for organizing the conference. It's all credit to Professor Panigrahi, but
Sorry, honestly speaking, let me just add. Honestly, this time I have not been much disturbed because I find my major worry is this connectivity. With Aradhya, Avinash, and this couple of other students around, they take this early morning, Aradhya and Avinash, then Sarang and Nitish, they come in, and then students come in. I don't have to bother at all. That's why
But I think the online thing is so beautiful that there is no car sending to pick up guests and drop them off, and all those things are not there. You switch on the computer and they are there. So that's beautiful.
And also this Soren
Yes.
and Amit.
Yes.
Soren, for example, sitting at home, don't have to tell him anything. Perfect, find out who is there, who is not there, and sending them invitation without prodding, completely on their own.
Yes.
So I have been able to quite listen to talk in a very relaxed way. So in a sense, very enjoyable.
No, I think you did a commendable job, and it's very difficult. And practically you went through all the talks. You were there in every talk. That's almost an impossible job, seriously.
I am a selfish person. If I am spending so much of time, I should learn.
No, thank you very much, Prashant, really. And maybe you want to say something to the party. It's really incredible. Also, these 100 participants I see.
Really incredible.
You see, at this hour, 100 participants is very beautiful. I mean, maybe you...
They really have been inspiration. The kind of questions they asked. This yesterday, day before yesterday, almost all the speakers are very impressed. This guy, Havasta, Franco Nuri, then this Sponar from Austria, they are quite impressed. He said, these guys are asking meaningful questions. They have made our day. Utpal is there. Hello, Utpal, how are you?
Yes, sir. Big congrats. Big congrats for the whole program, and hats off to you and your team.
Yes.
He is much more than arranging conferences, because it's a very long time, 34 days. And all of you are constantly there. And I can see even in the last talk, a lot of participants.
Yes.
Is Alok around? Is Alok also around? No.
Alok is probably tired.
He's tired. He's like taking rest.
Yeah. Aniket, are you around? Aniket Patra. Maybe we can say goodbye to you.
Oh, yes, sir. I'm around.
Yeah, Aniket is listening carefully.
Yeah.
And you are welcome. So come sometime when things improve here.
Yes. I haven't been home for a very long time now. So I'm literally stuck here in Europe. And so another thing is I haven't even got my vaccine. So,
Okay.
you can't, if I go home, I'm afraid they will not allow me to come back. So kind of stuck in that sense.
But because of precaution, you should take vaccine.
Yeah, no, I definitely want to take vaccine, but I'm right now in Denmark, and in Denmark, they initially, they completely banned this use of AstraZeneca and this other Johnson & Johnson vaccine. So they are only reliant on Pfizer and the Moderna vaccine. So this is quite slow. Vaccine rollout is quite slow here. So I think my appointment here on 18th of July. So the first dose for vaccine. So I will be completely vaccinated by the end of August. And I hope to at some point travel home, because my parents are also quite impatient with me, because they don't understand, they're like, yeah, you are doing very important work, and they don't care. It's just come home. But yeah.
You are from Bankura, right?
Yes.
Tarak Nadde and you are from the same village, right?
Yes. I know Professor Day, because my father knows him actually better. So, but I haven't personally met him. But
he knows you quite well, actually. Yeah.
I see. No, I know about his work, because he works. I think he worked with Professor Agarwal, G.S. Agarwal, quite a lot. Yes. And all these works that I showed, these are related to those kind of works. So it's small.
Yeah, exactly. Your work is very much related to Agarwal's recent works.
Yeah. Oh, this is quite fascinating.
When you come here, I would like to hear from you. How was it working with Alsuler? Boris Alsuler.
Yeah.
Must have been some experience, huh?
Yeah, no, it was quite an experience. I can tell you stories. Yeah.
Okay.
You don't want to tell stories online about him, or do you?
No, I mean, they're not scandalous stories, but very intriguing stories. I mean,
I can imagine.
He is quite a fascinating character.
No, man. And for us, I think mesoscopic physics is really one of the fathers of it.
Yeah.
Right. The only one thing that I can tell you is that, being the guy who proposed MBL, many body localization, it's very, very, like, it's damn near impossible to localize him in like real space. Like, it's very hard to find him at one particular space at one time. Like, you know, it took all our effort to essentially localize him to have discussion. So that's the one thing that I can tell you. So yeah, like, it took all the expertise of my PhD advisor, who is a direct PhD student of Professor Altshuler.
I see.
To track him down, because you know, he doesn't answer phones. He doesn't even like pick up. He doesn't answer emails. So it's quite a science to localize him to have discussions.
Amazing.
But once you do, then the discussions are absolutely fascinating and absolutely amazing.
You know, it's sort of close to a genius. I mean, you know, the kind of thing what he has done, amazing actually.
Right.
Yeah. Okay, so Soren, let's call it a day.
Yes, there are lots of thanks for you. Lots of messages for you, Prashant. Lots and lots.
I'm really impressed by the participants. Thanks to their energy, we have been going on for so long, otherwise it would not have been possible. Amazing amount of energy you guys have. I mean, only I can say, God bless you. Keep your heads up, do good science. That's what I can tell you, because these talks have been excellent. I learned a lot, and I hope you have learned a lot. And keep it up. Hope to meet you soon somewhere. And many of you will, I'm sure, go on and do your higher studies. And some of you probably in quantum science. If not, this will still help you. Okay, goodbye.
Okay, Prashant. So we close it. Okay, Krishanu, thank you. And all the speakers of this session. Okay, we close the session now. Bye-bye.